Okay, let's go over this one. Now, the accompanying data represents the weights of various domestic cars and their gas mileages in the city. The linear correlation coefficient between the weight of a car and its miles per gallon in the city is R equals negative 0.973. The least squares regression line, treating weight as the explanatory variable and miles per gallon as the response variable, is y hat equals so forth, so forth. Okay. We're first asked what proportion of the variability in miles per gallon is explained by the relation between weight of the car and miles per gallon. What we're talking about here is the coefficient of variation, and that's the r squared. Now, we can actually calculate that in a couple of ways. First thing we could do is we're given r, and so we could calculate r squared just by taking that number and squaring it. I think we can do this without actually doing any stat crunch. So I'm just going to do that. I'm going to pull up a calculator, and I'm going to take this. So it's going to be 0.973 squared. So I have 0.946729. I'm going to just check and see. I want one decimal place. So 946 rounds up to 94.7. 94.7. 94.7%. All right, that's how you interpret the r squared. It's converted to a percentage, and then that represents what percentage of variation in your response variable is explained by your explanatory variable. Now, we could actually open the data in StatCrunch and we could create the scatter plot, but I think we can figure out which residual plot. The residual plot to verify requirements of a least squared regression. Choose the correct plot below. The residual plot. And actually, residual plot. These are. I was going to say that we could find the. We could estimate this scatter plot from just the data, but this is looking for residuals. So we're going to actually open up StatCrunch and get this from StatCrunch. I'm going to open the data table, and I'm going to export the data to StatCrunch, and we'll create the residual plot and see which one it matches with. All right. So under what we need to do is we have to first create the linear regression. So under stat, it's stat regression, simple linear regression. Our x variable, as we said, is the what was it? We want to have the weight of the car is the explanatory variable. I probably could have known that because there's only the other one is just the car. That's an index. The weight is x, miles per gallon is y. It was obvious because it was x and y. All right. Now, what I want to do is just scroll down a little bit, and I can graph the residual, not the residual index plot, residuals versus x values. That's the graph that I want, because I want the x value, which is the weight, as my horizontal variable, and I want to plot that against the residuals. And that's all I want. I'm going to click compute, and I'm going to get the residual plot in my second window. So you can see I can go between windows. My second window is my residual plot. I'm going to put this to the side. I'm going to put it on that side of it and just see which of these it matches with. And it looks to me like this matches with the fourth choice. The first choice, I think that might be if you were to do, if you were going to plot the residuals against, I don't know what that is actually. If that's inverted or something, flipped around. I don't know how they got that plot, but anyway, I know it's wrong. I'm going to go with D. Interpret the coefficient of determination. Oh, I called it the coefficient of variation earlier. Sorry. Coefficient of determination, and comment on the adequacy of the linear model. Okay, so this is that 94.7% we mentioned earlier. 94.7% of the variance in my y variable, gas mileage, is explained by the linear model. The least squares regression model appears to be appropriate based on the residual plot. I would say definitely. The reason I'm saying that is because a residual plot that has essentially no pattern to it is a very good thing to have. And also the fact that my r squared was so insanely high, 94.7 or 0.947. You never get that unless you have a really, really strong relationship. Anyway, that's that. I'm gonna go. I wonder if I want to. Yeah, I'll check answer. Input is correct, 100%. Oh, that's nice. Let's move on to the next one. Suppose a least squares regression line is given by y hat equals so forth. What is the mean value of the response variable if x equals 20? So what I'm asked is essentially, here's an equation. I want to plug in a value for x and see what I get for y. Now I'm going to do this again in the calculator. Just the regular Windows calculator will do. I don't think I'm going to move to scientific mode because I've got parentheses at my disposal here. I'm going to put in 4.302 times my value of 20, a minus 3.293. And see what I get, 82.747. I'm going to copy 3 decimal places and paste it over. 82.7. That's it. So let's check our answer. It's 100% correct. That's great. So that's all it is. If you're asked to predict using linear model, you just plug in your x value and see what you get. Of course, if you have a more complicated linear model, like a multiple regression, it's a little more complicated. But basically, you just plug in all the variables on the, in the expression, and then you'll see what it comes out to be. Okay, so a pediatrician wants to determine the relation that may exist between a child's height and head circumference. She randomly selects 5 children and measures their height and head circumference. All right, so first thing we're asked to do a simple linear regression, okay? So what do we have? We asked for B0 and B1. B0 is the intercept estimate. So we're asked for 4 decimal places, 13.422388. So we have to round it up. We have to round it up to 13.4224. That's rounded up. The slope is going to round up as well. Or what does it round? So we have 0.14925, which would round this up to 1493. Let's see. Now we're asked for the standard error of the estimate. That is also called the standard error of the standard deviation of the errors, or the residual standard deviation. It's given in the output up above. It's called the estimate of the error of the standard deviation. And I'm going to want 4 decimal places. And again, I'm going to round up. So I'll type that in. 0.0599. Now I'm told a normal probability plot suggests the residuals are normally distributed. Now we're going to get SB1, which is the standard error of B1. That's the standard error of my slope estimate. And that's given in the table. And if I want 4 decimal places, I can copy those over because I don't have to round this one up. Now, a normal probability plot suggests the residuals are normally distributed, just like we said. We want to test whether a linear relation exists between height and head circumference at alpha equals 0.01. Level of significance. State the null and alternative hypotheses for this test. This is always so if we're interested in whether a linear relation exists, we're testing whether the slope is or isn't 0. The null hypothesis is going to be that the slope is 0, and the alternative is the slope is not 0. Beta 1 is the parameter that represents slope in the real life model. So we're asked whether the null hypothesis would be that beta 1 equals 0. The alternative is that beta 1 does not equal 0. Now the p-value for the test is given right beside the t-stat for the slope. It is 0.0075, so I'm going to round that up to 0.008 it rounds up to. And now the conclusion, because this is less than our alpha level 0.01, we can reject the null hypothesis. We want to conclude that a linear relation does exist between child's height and head circumference. Yep. And we want to now construct a 95% confidence interval. So I'm going to go back to the options and edit the options because I want to change from a hypothesis test to a confidence interval. Click compute, and I'm going to expand that so I can see it. Now for the slope, I have 95% lower limit and upper limit. And those are confidence bounds, and I want 3 decimal places, so I'm going to need to round those. The lower one is 0.076, and the upper one is 0.223. So obnoxious. Okay, 0.076 and 0.223. Now we want to do a prediction. Suppose a child's height is 26.5 inches. Okay, so we'll go back to edit our options for this and scroll down a little bit. We're going to a prediction of y based on x value. We plug in the x value, 26.5, and we click compute, and it's going to predict our y value for that. And that's going to be down below in our output. X value 26.5, y value 17.3776. Well, okay, we want 2 decimal places, so 17.38 is going to be our 17.38. And if I didn't make any typos, let's check our answer. See, 100% correct. That's great. That's what I want to see. Let's go on. Problem 25. Okay, as concrete cures, it gains strength. The following data represents the 7-day and 28-day strength in pounds per square inch. It looks pretty similar what I want to do with this one, so I'm going to just try to go through and hopefully not take too long to do it. I'm first asked to, well, I want to do, again, another regression, a simple linear regression. My x variable is 7-day strength, and my y variable is 28-day strength. And I'm going to, again, just click compute and get my results. So I want to take 1 decimal place for my intercept, 2438.6. But for the slope, I want 4 decimal places, 0.6871. I have to round it up. This is probably the trickiest part of it, is just rounding to the right decimal places. For the standard error of the residuals, that's up at the top again. That's going to be that 102.3, or actually it's going to be 102.4, rounded to 1 decimal place. And then we're asked to find the standard error of the slope, and that's given in the table. And I want 4 decimal places, so 0.1047, rounded up. Everything's rounding up, it seems. It looks like the same, so we're asked, again, the same exact question, test whether a linear relation exists between 7-day and 28-day. It's testing whether the slope equals 0 versus the slope not equal 0. Beta 1 equals 0. Alternative is beta 1 not equal 0. And the p-value, again, it's right there in the table. And at 3 decimal places, it rounds to 0.008. What's the conclusion that I can draw? Well, I want to reject the null hypothesis because that's low at a 0.05 significance level. A linear relation does exist, so we want to reject null hypothesis, conclude a linear relation exists between the 7-day and the 28-day strength of a certain type of concrete. Okay, that's it. Now we want to do, I'm going to go back to edit. I can see, again, we're asked for a confidence interval, and while I'm at it, I'm going to put in my X value of 3000 psi, because I'm going to need both of those things. You can see the slope has a 95% confidence interval bound of 0.354. I have to round to the nearest 3 decimal places. The upper bound was 1.020. And then a good estimate for the 28-day PSI, if you had 3,000 PSI on day 7, is given down below in the table, and it's 4499.79 rounded up is going to be 80. And that's it. Let's just check and see if I got that. Oh, 100%. That's good. Let's move on. All right. The data in the accompanying table represents the population of a certain country every 10 years. From 1900 to 2000, an ecologist is interested in finding an equation that describes the population of the country over time. Let's look at the data. Okay. Open it in StackCrunch. Now, determine the least squares regression equation treating years explanatory variable. Choose the correct answer below. All right, well, let's see. Let's go to stat, regression, simple linear. And I'm going to pick year as X and the population as Y, and we're going to compute. And now we have let's see. Let's see. It's actually given up above. You can see it's negative 3723,129.6, which could be rounded off to, it's like basically negative 3.7 million plus 1994 times the year X. So you want to make sure that you have positive plus 1994 is the coefficient of year X, and that's happening in the first equation here. A normal probability plot of residuals indicates the residuals are approximately normally distributed. Okay, I believe it. Test whether a linear relation exists at, between year and population. Well, we can look now at it's the same as the last one. It's always going to be testing beta 1 equals 0 versus beta 1 not equals 0. And the p-value is given in the table. And rounded to 3, because it's less than 0.0001, that's essentially, it's close, that rounds to 0. P-value isn't exactly 0, but it rounds to 0. The appropriate conclusion is to reject the null hypothesis, and then there is sufficient evidence to conclude a linear relation exists. There is enough evidence because the evidence is in favor of the alternative. Draw a scatter diagram. What does the scatter diagram look like? It's always actually, the scatter diagram is like a little bonus whenever you do a linear regression. Click this little arrow at the bottom, and you can see your scatter diagram. And so the points are kind of dipping down and dipping up. It looks like B is the right scatter diagram. Plotting the residuals. If we look at the residuals, let's go back to the options. And I want to look at the residual of versus X values. And if you look at that, this is what these look like. Now, this is not a very nice residual plot because I see a very distinct pattern, which tells me that a linear model is not actually the right kind of model for this data. Some sort of curved regression line is better, like an exponential curve or something like that. But anyway, this is my residual plot. Does linear seem appropriate based on the scatter? No, it does not. The moral is, even though, let's see, in my words, even though there is a significant linear relationship, that doesn't mean that a linear model is the best model. Sometimes the residuals might like that might be violated because like there's definitely an increasing trend. So let's see what the choices are. The moral is that explanatory variables may indicate that a linear relation between two variables does not exist, even though diagnostic tools such as residual plots indicate that the linear model is appropriate. No, that's not the moral. The moral is that inferential procedures may indicate that a linear relation between two variables exists, even though a diagnostic tool such as a residual plot indicate that linear model is inappropriate. That seems pretty good so far. Let's see the third one. The moral is that inferential procedures may indicate that a nonlinear relation between the two variables exists, even though, no, that's not the moral. I mean, my take on it is that actually a non-linear model would be better, but that's not what this told us directly. Like, the hypothesis test on the slope said that, oh yeah, it's definitely a significant linear relationship. But when you look at the residuals, you realize, oh, it's not a linear relationship, it's a curved relationship. And you can get that from the residuals. Anyway, let's check our answer. Yep, 100% correct. Let's move on. Let's wrap this practice test up. Suppose there are n independent trials of an experiment with k greater than 3 mutually exclusive outcomes, where pi represents the probability of observing the ith outcome. Okay, so this is like, for example, if you're spinning a spinner with like 5 colors on it, the probability that each color comes up would be, like for color 1, 2, 3, 4, 5, it would be P1, P2, P3, P4, P5. And you're spinning it n times. K is the number of colors, n is the number of spins, pi is the probability or proportion of the spinner that is for color I. What would be the formula for expected count in the situation? So the expected count for every color would be the probability of spinning that color times the number of spins. So it'd be n times pi. That would be the formula for the expected frequency for each color. Yep, that's right. And finally, what are the residuals? What are the requirements to perform a one-way ANOVA? Select all that apply. So let's see. The sample means must all be equal. That's not a requirement for a one-way ANOVA. That's that's the assumption of the null hypothesis when you're doing an ANOVA test, but it isn't a requirement to do the test. That's just an assumption. That's the assumption that you're testing. Actually, we're not testing the sample means being equal. We're testing the population means being equal. Sample means are never going to be equal because sample means are continuous random variables. They might be close, they might be far away, but that doesn't matter. Populations must be normally distributed is indeed one of the requirements. That's a requirement for the test. Sample size for each of the k samples must be equal? No. We don't need to have the same sample sizes. Those can be different. That's not a problem. There must be k simple random samples, one from each of k populations, or a randomized experiment with k treatments. Yes, that's one of the kind of the ideas of ANOVA. And k is 2 or really usually 3 or more. So every population that you're looking at has a sample from it. And the samples can have different sample sizes, but you have to have a sample from each population you're testing. Let's see, the within sample variability must be less than the combined variance of each group. No, that's not a requirement of ANOVA. The k samples must be independent of each other. That is, the subjects in each group cannot be related in any way to the subjects in the second group. Yes. We need independence between the groups. That's an important requirement. And finally, populations must have the same variance. That is, each treatment group has population variance sigma squared, and that is a requirement. We require or assume that at least approximately the populations have the same variance. That's part of the assumptions of doing an ANOVA test. So finally, is the one-way ANOVA test robust? It's robust against normality, especially if the sample sizes are large. So we can say, yes, small departures from the normality requirement do not significantly affect the results. That's the robustness of the ANOVA is related to the assumption of normality. Great. Okay, so that's the practice final exam, and that should give you a good idea of what you'll see on the regular final, the real final. Bye.